Okay, so what we'll do is we'll finish off the work on external flows today. Maybe recap a little bit about the big picture of what we're trying to do. And also maybe look at some things that are fluids in the news just to get things going. The one thing amazed me from this recent typhoon, which I guess was happening this time last week, last Sunday, last weekend, was this is a picture of the storm surge, which is, to me, incredibly fast and incredibly high. I mean, you think of a storm surge as a tidal surge kind of rolls in, the tide comes in, you just walk away from it. But that clearly is faster than that. And so apparently it was a 20-foot storm surge in some places. And so tough to be able to get away from that, I think, right? If you weren't quite getting rid of it.
Community continues to pray for the victims.
I guess this is overprinting my voice, and perhaps I'll turn it back down for that reason. So the kind of conventional wisdom for tsunamis and storm surges are that I was struck after the Japan tsunami in March of 2011. I happened to be in LA for a meeting, and I was driving around in Huntington Beach, and I realized that when you drive around in LA and Huntington Beach, you drive for probably 2 or 3 miles where it's absolutely dead flat before you get to the ocean. Which means, of course, that if the ocean comes in and there's all these very expensive scooped-out canals with condos where you can keep your boat next to your condo, and they're incredibly vulnerable to anything that comes across from the Pacific. But, of course, there's this hazard as well from landslides on the east coast of the U.S. and tsunamis that can result there as well. There was a tsunami after the Alaska earthquake in 1964, for instance. And so quite vulnerable, right? You drive and it's dead flat. And so the conventional wisdom, which I was getting to, is that what's bad for LA is that all these are single-family bungalows, one-story homes. And the conventional wisdom, if you're in an area at the coast where there's a tsunami, you just go, it's kind of vertical retreat. You go up into a tall building. The water washes in. If you're above the second floor, you're probably fine. You might remember from some of the footage we looked at, some of the photos we looked at the beginning of this class, there were schools which were actually hit up to their 3rd story. 4th story was fine, and so they are quite tall, these things. So a story is about 10 feet on average, so 30 feet or 10 meters, 9 meters, I guess, once they have the run up onto the shore. So interesting natural phenomena driven by natural phenomena. I'm sure you've seen this, and so I guess the reason that buildings survive is if you think about the stanchions or the beams, the columns that they have, even if you wash the walls out, those columns actually have a relatively small sectional area, and so the kinds of things we're talking about in terms of external flows, the same things that makes a wing work and a plane fly, are the same things that would break, for instance, buildings down by the force of fluid acting dynamically as it washes past those individual columns. And so it's relevant to the kinds of things we're talking about today. Many of you will have seen this in your physics classes, I suppose. Galloping Gertie, the Tacoma Narrows Bridge that destroyed itself. Again, the phenomenon is driven by, this is a 40-mile-an-hour wind which rushed over this bridge. The unfortunate design was that the resonant frequency that the wind set up in the bridge was exactly the resonant frequency of the bridge, and deformations build and build and build until it pulls itself apart. So the most obvious exposition of that is, I forgot to bring it today. If you take a ruler and you take it over a table and you ping the ruler, it vibrates at some frequency. The frequency is basically a standing wave. The wavelength is the length of the ruler, which is the critical frequency for it. If you shorten it, the standing wavelength is shortened by that amount, and you ping it, and it's a higher frequency, like a guitar string. And so a bridge is just the same as that. It has a characteristic frequency where most of the energy it vibrates at lives, and lots of sub-frequencies below that, higher frequencies above that would fit into it. And if you happen to excite it at that particular frequency, then what happens is you get some kind of growing disturbance which grows until it falls apart. And so perhaps we'll look at that in a little while also. Airbus 380, no, I'm not going to do that. This is about testing it for flutter in the air, and it goes a bit long, so I won't do that. But again, so the reason that the bridge was put into resonance was the air flowing over it. It happened to excite it by von Karman Vortex Street, which we'll look at also. Seems like a few years ago, but I guess it's much longer than that now. There was a crash at Orange County Airport in LA of a small executive jet that came in behind a 757 like this. And so what happens with any aircraft is it provides lift by the Bernoulli principle. If you looked at the Coanda effect in the funny video we had on one of the previous movies, 12.1, I guess it was 12.1, is that they provide lift. And so with that lift, it also sheds vortices off the wings, and you can see those as it goes by and lands in this particular case. But this was an executive jet which was landing too close behind a much larger jet with very high lift wings. The vortices which were thrown off the wings were large enough that it actually slammed the plane into the ground, and with the ensuing crash that resulted. I'm trying to think also, the other thing that happened right after 9/11, yeah, you certainly were all alive for that. There was a plane crash in New York City. It was worried that it was a kind of a repeat of what was going on September the 11th. It was in maybe November of that year. And what it was a plane that flew through the wake of another plane. It was on its way to Dominican Republic, as I remember. And it flew through the vortices from this other 747, and it snapped the tail off an Airbus. And it crashed into one of the neighborhoods where, ironically and sadly, many of the firefighters, the first responders, live traditionally in New York City. And so the fact that you're lifting a plane up means it's a huge weight that you're applying, or force that you're applying to be able to do that. And that's a disturbance in the air, which is then available to be able to wreak havoc with other structures that happen to flow through that in an unfortunate way. This was sent by one of the students, Matt, in this class. It's of Formula One cars and how they test them to be able to look at designing the cowlings and the aerodynamics for them by having all of these arrays of pitot tubes to be able to measure pressures and velocities. And so if you want to be able to design the cowlings and the coverings for the engines and the parts and the wheels so that you actually reduce drag and maybe provide negative lift, forcing it down to the ground, then you can evaluate the airflow in real time in the practice laps to be able to test out new designs so you get that. Used to be, and certainly probably in your time as well, so you guys are 20, so you've been around since the early 1990s. Used to be that Formula One cars were these wedges that were covered with aerodynamic surfaces and physically forced them down onto the ground so they could drive really fast. They changed the rules to make it more challenging. I presume they must define now exactly how much square inches, how many square inches of surfaces you can have in some way. I'm not sure exactly how. What else? Other interesting things with planes. Recently, there was an experiment to basically take a Hercules-like military plane up into the air, have it dump out a whole bunch of volcanic ash, and have some planes, one fly through it, but also a couple of them try and detect it by using forward-looking radar. And that's something that was just done maybe half a dozen days ago. And they're successful. So Airbus 340-300 was a plane that has some kind of sensors, picked up the ash from 60 kilometers. Of course, the problem with ash is it gets ingested into the air, into the engines, and it's abrasive, and so it destroys the fan blades. And if there's too much ash, of course, it will stall out the engines. One well-documented example from, again, I think a decade ago, a KLM 747 flew through an ash cloud in Alaska. So the Great Pacific Route, you go up from San Francisco to Tokyo, you go up along the west coast of BC, along the Aleutian Arc and down the Kamchatka Peninsula on eastern Russia, Sakhalin Island, and into Tokyo or Beijing. That's the Ring of Fire. And so this is one of the Alaska volcanoes, happily flying away, goes through the ash cloud, and all of a sudden the cockpit fills up with ash, all the engines cut out, and you're just gliding for a while. And they got the engine started, as it turned out, with lots of damage, lots of scored windows from the abrasion, from the ash, trashed engines, I'm sure, but they did get it restarted, and it did land successfully. And of course, this time last year, there was this guy, Felix Baumgartner, who was the guy who did the highest skydive. So he went up to 128,000 feet, I guess, so that's about 128,000 feet is 40,000 meters, right, of that order, 40 kilometers up, and jumped out. And of course, the rate at which he fell to the ground is governed by this balance between drag. You don't keep on accelerating. You're not in a vacuum. You're in air. And so as you fall, you have this competition between your weight acting downwards, your buoyant weight acting upwards. In air, it's not very much because the air you displace is very little mass, and the drag force that goes past you by the air that goes around you. And you reach some kind of equilibrium, some equilibrium terminal velocity. I think the terminal velocity of a person falling in air is something like a couple of hundred miles an hour. You don't accelerate. The question here was whether you actually go through the speed of sound, and I think he did. He broke the speed of sound. Speed of sound is probably 600 miles an hour, and so it's much higher than normal terminal velocity. And as we'll see today, perhaps the reason for that is that the density of air is much lower at higher altitudes. And so the velocity that you go through is regulated by that. And so those are kinds of things that we can look at in terms of what we're looking at in terms of external flows. And of course, the other thing related to these hurricanes and the winds we had last night, you can look at, one of the principal, I always think it's interesting that one of the greatest causes of deaths in hurricanes is not people getting blown over or hit by debris, it's actually freshwater drownings or being washed out to sea. It's freshwater drowning. So it's rain on land, swelling rivers that ultimately impact people who are inland rather than on the coast. But the other mechanism is, of course, by having a 2x4 picked up and thrown at you. And of course, that is a mechanism which is also driven by drag. And you can rationalize exactly what the velocity of that 2x4 would be as a function of the forces that are applied on it. And so those are the kinds of things that we're attempting to understand when we're talking about external flows. If you looked at the movies already, I'm not sure how many of you have or haven't, doesn't matter, you should do if you haven't. It makes the case that external flows and internal flows are really very similar to each other. In internal flows and pipe flows, we're interested in figuring out what the velocity is or the flow rate in the pipe is as a function of the pressure that we apply. Typically, in external flows, we're interested more in turning the forces on a structure as a function of a known velocity of the fluid over it. But they're related in some way. And so let's just quickly summarize the approaches, if you like, in looking at this. And so basically when we're looking at external flows, we're interested in a couple of things. And we can figure out what the forces are. So typically we're interested in what the force applied on something is, a drag force, or the lift applied on something is. We can often think of it in terms of an airfoil, and actually lots of our examples were defined in terms of that. And we make the case only that if you have a velocity that impinges on a structure, we're interested in both the drag force, we've done it as a curly D, or the lift force as a curly L. The only thing that differs between these is that the drag force is in the direction of the flow, the airflow, and the lift is perpendicular to that. That's purely the definition of what these are. And so typically we're interested in figuring out what these magnitudes are, and we can do it by a couple of ways. We can get either the drag or the lift. They're a function of a couple of things. They're functions of the pressures that are applied to a structure, which we can use to calculate the force. Obviously, if you know what the force is, pressures that are acting on the tip of this, the tip of a rocket, you can calculate what the force is that you have to overcome to push it through the air. And we've talked about that in this class. They're a function of the velocity of flow, and they may change with time. But if you look at these two principal actors here, it comes really from looking at Bernoulli, and we've talked about Bernoulli. This is the pressure that's applied by killing a velocity. So from, say, v goes to 0. And so what we could do is we can write the two components of Bernoulli typically as equal to each other. And so if we change the velocity between an upstream location and a downstream location by some amount, we can calculate what the fluid pressure is that's created as a result of that. And if we know what the fluid pressure is, then we'd know what the force would be that's applied to it. So very simplistically, that's one way to do it. The second mechanism is that we can use velocity differently from here to define the frictional force. And for that, we merely can calculate that the shear stress that's applied to something, which might be, say, on the bottom of this airfoil, is given by Newton's law of viscosity. And so if we know what the velocity distribution around it is, as in this parameter here, and we know what the viscosity of the fluid is, we can calculate what the shear stress is. If we know what the shear stress is, we could multiply it by an area. So tau multiplied by some area would give us in this case, a drag force, right? This magnitude here. So very simplistically, that's what we're interested in. Two components. By definition, drag being in the direction of the airflow, major airflow, and lift being perpendicular to that. Could also be negative lift, as in a racing car. But those are the two major components that we're interested in. We can get these by, I guess I didn't really need to use that. The approaches we have to get this are by analysis. And we can either use closed form solutions, and there are some that we talked about in parts 12.1 and 12.2, 12.1 mainly. And we can also use numerical models. And we messed around also in 12.1 using a model to calculate what the forces were that were applied on an airfoil to be able to figure out how those scale as a function of the important non-dimensional parameters. And numerical models, well, we won't go back into it, but they're typically using Navier-Stokes equations, and they're really just using the things that we've done already in this class: conservation of momentum, conservation of mass, solving those equations in a discrete form to be able to come up with a distribution of pressures and velocities around a structure from which you can do these kinds of calculations. So that's one approach. However, a much more common approach, actually I guess probably becoming less common, is to do experimental work or dimensional analysis. And that's so you use a wind tunnel. And so if you do that, then all you do is you take a model plane, you make sure it's a scale model or a model wing, you flow air past it, you measure what these forces are that are applied onto it, and then you try and scale it in some way according to appropriate non-dimensional groups. And you'll notice that these dimensional groups here, this is, it's not quite an Euler number, but it's very close to being it is an Euler number, right? This is an Euler number. So a force divided by an area is a pressure. And a pressure divided by density and velocity squared is our Euler number. And so these coefficients of lift and coefficients of drag are convenient ways for us to be able to define the quantities, to be able to do something quantitative with external flows. So the punchline of everything we'll have talked about up till this point in this section, in the previous two sessions, is that we can draw a figure. And this figure will look something like a Moody chart. And it will be scaled with Reynolds number. So in other words, this scales with increasing velocity, if you like. Reynolds number is what? A velocity, a density, a characteristic length, and a viscosity, ratio of inertial forces and viscous forces. And when we talked about the Moody chart, we drew it in terms of a friction factor, but let's modify it. You can also draw it in terms of a friction factor multiplied by length over diameter. And we've done this analysis in one of the previous classes. This is equal to, as it turns out, a pressure divided by a half density times velocity squared, which is the same as, say, let's call this P a force divided by a half density velocity squared times an area. So I think if there's, I'll make it slightly smaller so both fit on at the same time. It's exactly the same as this. So this is the same as either a coefficient of lift or a coefficient of drag. And so by definition, this is an Euler number, it's non-dimensional. It's exactly the same as taking a friction factor and just multiplying through by length over diameter. And so if that's the case, we'd expect to have two parts to this. We talked about three parts when we did it for Moody charts, but let's talk about just two now. Let's ignore the transitional region. So this is laminar. This may be, say, 10 to the 2 Reynolds number. If you've looked at the previous videos, then the behavior for a sphere, this coefficient of drag is equal to 24 over Reynolds number, where the Reynolds number is defined in terms of the diameter of the sphere. Sorry. I'll write it out as diameter. This is squiggly d. I can't draw it very well. Do some little things on this. This is a force. So this is this squiggly d. Not to be confused with the diameter of this particle. And this is turbulent. And so if you remember one thing from today, remember this figure and the fact that it's divided into two different parts. It's important to think about it in two different parts because that defines exactly how we deal with these things. And the important observations are that in this portion here, this drag or lift is due to frictional or viscous drag or lift. We use them synonymously, right? Just by definition. So frictional viscous, it's due to viscosity. If you drop a coin or a bead into honey or molasses, it moves slowly. It moves slowly because the viscosity is dragging against the side of it and stopping it from moving. And so that's the same as low flows in pipes. It's governed by these frictional resistance. Yes, go ahead.
Diameter, it says CG is equal to 2. What does that say?
It should say Reynolds number. Sorry, R. I left out the E. So it's not CG, it's a coefficient of drag. Okay. CD is equal to 24 over Reynolds number.
Okay, great.
No problem. Thank you. And so the other regime on the other side of this is pressure drag. And so in other words, you fire a hose at me, the pressure of the velocity of the hose destroying itself on my chest pushes me back. That's killing that velocity. Same with an air jet. Same process. You're killing the momentum of that air or water, and as a result, there's a force applied on you. And so, for the same structure, at different velocities, you'd have this different effects. So at low velocities on a circular thing, you'd have the effect of viscosity. As you increase the velocities, so that killing momentum is now a much larger effect, now the behavior is dominated by this pressure drag. And so you see a couple of things. One is that in this regime, the drag coefficient is a function of Reynolds number, and that might be a problem for us in the same way it was difficult for us to figure out what the friction factor was if we didn't first know what the velocity was, because we need to know in this what the Reynolds number is to know exactly where on this chart we are. And the easy part here is that CD, or coefficient of lift, is constant. So in other words, if we know that we're in this regime here, we just pull a number off and we can quickly use it in here. We know what the velocity that we're killing or we have applied on our system. We know what the characteristic area is. We know what the drag coefficient is just by going across here. And therefore we know everything to be able to calculate what this is, either the drag or the lift. So that's it. So if you remember something today, remember that there are these two regimes that we have to deal with to be able to make a calculation. So let's try making those calculations. Okay. So we're going to do an example on, first of all, one that encompasses both of these, which is going to be Tacoma Narrows. We're going to do an example on this, which is Stokes settling. So if you want to, we'll get to it later. And we'll do an example on this, which is a hailstorm. I should actually know how to count, right? 1, 2, and 3. So that's what we'll do today. Tacoma Narrows we already looked at, right? Galloping Gertie, donors killed. It's a bridge in the 1950s, destroyed itself. And so the question is, what is going on, and how does this diagram relate to this in some way? Well, the one thing that this diagram relates to is that you should surmise that from looking at this, the change in this drag force as you go from low flow rates to high flow rates, the reason that this changes its shape is that the flow field around this sphere, if you like, is changing as a function of the velocity. And if you go back to this point, where is it? Actually, it's right after it. I think it is. This. So this is a figure that illustrates this. So this is this coefficient of drag as a function of Reynolds number. This is our 10 to the 2 point. This is our equation for a sphere, which is equal to 24 over Reynolds number. If it's not written there, yeah, I guess it's written there, right? And you see as you increase the flow velocity for a cylinder or for a sphere, you get this transition. This comes directly from the book. And this is showing the flow field that you get around a cylinder, just because a cylinder is easier to look at in a wind tunnel because you get multiple planes going through it. These points here at very low Reynolds numbers, A, B, C, D, and E, are just transitional Reynolds numbers where it starts with this nice creeping flow around it. As you increase the Reynolds number, you get this separation at the back. Here there's a stagnation point. Here there's a separation point. But as you increase the Reynolds number, you get a flow that has this symmetric eddies behind, which are these circulations. You increase it to this point at 10 to the 2 Reynolds number, and you get what's referred to as a Kármán vortex street, not sheet, but street. And the idea is that you shed off each of these vortices behind it, first from the bottom of the sphere, then from the top of the cylinder, then from the bottom of the cylinder, then from the top of the cylinder, sequentially. So every time one of these vortices leaves it and goes downstream, there's a little jog that it gives to the cylinder. And so if the cylinder is able to move, it will jerk it around in a small way. First in one direction, and then in the other direction. And so this occurs at a very specific, experimentally, a very specific Reynolds number, which is a Reynolds number of about 10 to the 2, which is equal to, however we define Reynolds number, as density, velocity, diameter of the cylinder or of the sphere, and its viscosity. And then as you increase the velocities even more, then you get a much more muddled approach where you have these vortices shed off the back, but they're small and it's just a wake which is kind of nondescript. But here you get this very distinctive pattern. This has been shed off first, then this one second from the top, then this one third from the bottom, then this one fourth from the top, etc., and it'll keep on going. And it turns out that because of this flow, you get a very specific excitation given to this, and these will be shed off in a frequency, and it's in here somewhere, and the frequency it's shed off is this. It's shed off at a frequency which is given by a non-dimensional number, which is Reynolds number. We said this number, when this occurs, is about 10 to the 2. So 20 divided by 10 to the 2 is about 0.2. 1 minus 0.2, well, in my math, that's about 1. And so the frequency that you expect this to occur at, you can just calculate from these experiments. And they're just done, well, von Karman was a famous fluid mechanician from Caltech in the early 1900s. So if you know the velocity of flow, you know the diameter of the particle, you can calculate what the frequency is. And so for our particular case of the bridge, I would guess that probably the structure that was causing it, it's not the suspension wires that are doing it, it's the deck. And so what this is there's some characteristic size for the deck. You release a vortex from the top, from the bottom, from the top, and they all get carried downstream. And so if you're calculating what the frequency is for this, then you should use a characteristic dimension of this deck. If we looked at the movie we had, you can get some ideas of this. I guess it's this one, right? Do I want to do this? Let it go. So you see it. So there are two carriageways. I don't know what a carriageway is. It's probably about 10 feet wide, right? So carriageway is 10 feet. There's the Puget Sound, which it crosses in the northwestern part of the U.S. in Washington. So carriageway is probably 10 feet. Two carriageway is 20 feet. So that's about 6 meters total. So I don't know. So I imagine the width of this is of the order of 10 meters, something of that. The depth of the box, which I presume is the main controlling dimension, is probably half of that. I don't know. So, but it's of the order of 10 meters when it's doing this. And so we should be able to calculate from this what the magnitude of that would be. So if this is about 10 meters, it's probably less than that, right? But order of magnitude. Then this is, this velocity was 42 miles per hour. So if I've learned anything from this course this year, meters per second is about half of that. It's about 20 meters a second. And so it's about 20 meters per second divided by 10. So that's 2 meters a second. 0.2 of that is 2 times 0.2 is 0.4. So it's a frequency of about 0.4 per second. So that means one twist every 2 seconds, right? That's or 2.5 seconds. So I don't know how good that is, but if you look at this, well, that's not bad. So I guess we needed that part. We needed exactly that part. That was perfect timing. 1,000, 2, 1,000. Yeah, it's of that order, right? And so it's not dependent. It's dependent on the velocity, but it also has to be in a very specific range of Reynolds number, which we must be in this particular case. And I'm not sure what else we could calculate. I suppose if you wanted to, since we know that it's occurring and it's actually twisting, we know it should be at a Reynolds number of about 10 to the 2. And I suppose if we wanted to, we could calculate, if we know the velocity, We know the density of the air. I guess we could calculate what the characteristic dimension is just by using our expression. And so since we know that Reynolds number is equal to about 10 to the 2 for this to happen, and that Reynolds number is equal to density and velocity and the size of the bridge, then we know the density of air is 1 kilogram a second. We know this is about 10 to the minus 5 Pascal seconds. We know the velocity is 20 meters a second. We could calculate what the characteristic D is. I'm not sure what that is. Anyone do that quickly? I guess that's 1 kilogram, so it's 10 to the 6, 10 to the 5 rather, times 20 meters a second, divided by 10 to the 2. Looks like a big number, right? If you do that. So in other words, the diameter of the bridge would be equal to 10 to the minus 5 times 10 to the 2 divided by 1 kilogram per meter cubed, which is air, divided by about 20 meters a second. Don't like this. So 20 meters a second is about 10 meters a second, so that's 10 to the minus 1. So 10 to the minus 6, no, 10 to the minus 6 times 10 to the 2 gives us 10 to the minus 3. Is that right? Oh, that's pretty small. That's millimeter. So is that right? Does that mean it's working on the bridge, the guy wires or something, rather than the bridge deck? I would never have thought that. But anyway. So I wonder how much latitude there is in terms of 10 to the 2. Certainly this equation isn't very sensitive to the magnitude of this, so long as it's big enough that this is basically 1, right? And so I guess it depends how long a span this is on this figure as to whether it's right here or whether it can be, here this is 10 times larger and this is 100 times larger. So maybe there's some latitude in this in terms of the number that we should use. Don't know. But anyway, so you can use it to be able to evaluate that. And so that's one particular case where I guess we've known what the Reynolds number is, because we know that for this to occur, we have to be at a number on this chart which is appropriate for that magnitude. We said there are two other behaviors that we should worry about. One is that we should look at the case where the drag coefficient is a function of Reynolds number, and one where it's independent of Reynolds number. There are two examples in the book that basically do that. You can look at them at your leisure, but they require two different approaches, I guess. That's one of the reasons for dividing it up into these two things. If we have creeping flow at very low velocities, then one way in which you can actually figure out the grain size distribution of very fine particles is to dump them into water and see how quickly they settle. You use the velocity at which it settles to be able to evaluate the particle diameter by what's referred to as Stokes settling, after the famous fluid scientist, don't know his first name, Stokes, who Navier-Stokes equations are named after. And so the approach is relatively straightforward. We work out what the drag force is that's applied by the shear forces that are applied on this. And so you can just do a force balance, which is the drag force, which is acting upwards, squiggly d, the buoyant force, which is the fluid that's displaced by this sphere, which is F sub b, and the weight of this body, which is forcing it to settle. So those are the three components. So the weight has to be counted by the drag force and the buoyant weight. The weight is just going to be the volume multiplied by the unit weight of the solid. The buoyant force is just going to be the volume multiplied by the unit weight of the fluid. And the drag force is just going to be given by this expression. Coefficient of drag is equal to squiggly d divided by convention, it's a half density times velocity squared times an area, So this half is just there by convention, because it comes from a half v squared. And so what we like to know is what the value of CD is. Well, we know that the coefficient of drag is equal to 24 over Reynolds number. So we don't know an actual magnitude for this, but we know it's a function of Reynolds number. And Reynolds number is equal to a velocity multiplied by a density times, let me do lowercase d as diameter so we don't confuse it, and a viscosity. So we don't know this velocity, that's what we want to know, and it turns up in here. Also, we want to know what this velocity is here, which we don't know. But we know everything else here. We're going to know what this is because we're going to equate this to the other forces that are acting on the body. The force acting up on this bead has to be the same, equal the force acting down on it if it's moving at a steady velocity and not accelerating, right? And so this drag force has to be equal to the weight minus the buoyant force. The buoyant force actually is quite significant here because if this is a mineral grain, maybe the specific gravity of this is 2.3 and the specific gravity of water is 1. So it's 30% of the overall weight is the buoyant force. And so if we set the drag force equal to the weight which we can calculate and the buoyant force, then we have this drag force here when it's moving steadily. We have the drag force defined as a function of this, which is just going to be 24 over Reynolds number, and Reynolds number is equal to the velocity multiplied by the density multiplied by the diameter and the viscosity. I'm just doing the substitution. And so now, if we solve this equation for a magnitude of d that we know, which is equal to this, then we can solve for the velocities. One of these velocities cancels out, one of the velocities cancels out, and we can solve for the velocity. And so in that way we can calculate, if we go down through this, it's written down bottom, the velocity is some relatively small number. It's in millimeters per second. So it's very small. So it's going down through water. And so that's one solution then, where we're on this side, we think we're on this side of the line. So I guess what we should also calculate, we should check that the magnitude of Reynolds number is actually less than about 100. And if it is less than 100, turns out to be less than 1, then we're firmly on this side of the curve, and therefore it's a valid solution. I guess we're firmly on this side of the curve. So we're, this is 10 to the 0, which is 1. So we're up here, which is where the appropriate magnitude of this drag occurs. Okay. So that's the first kind, the more difficult kind. The second, easier kind is when we think that we're going at a very high flow velocity or the fluid has very low viscosity, like air, for instance. Almost always the cases with air are turbulent, and we're in this regime. And so the other example, as we mentioned, is for the making of a hailstone. Hailstones get circulated up in thunder caps by high upward flow velocities. They get lofted up and they get plated with ice as they go up in the very cold reaches up at the top of a cloud. And we do exactly the same now in solving the problem. The question is, when is the hail ready to come out of the cloud? Well, it comes out of the cloud when no longer the lofting velocity that keeps it aloft is enough because the hailstone's got too big and it drops out. And that will occur when this relationship is just on the edge of being violated. So in other words, the size of the hailstone, the buoyant force, which is negligible in this case, the density of air times the volume of the hailstone will be very small compared to the density of water multiplied by its volume. And so in this particular case, we can just solve for these two expressions here. Again, we can write coefficient of drag is equal to some drag force divided by a half density of the fluid. This is the fluid density times its velocity squared. If we know that the drag force is equal to a number, if we go up through this, in this regime here, for a smooth sphere, this is the magnitude of drag, and so you can just come along here and you pull off a number. Maybe it's 0.4. I think in this question they use a magnitude of 0.5, and so in this particular case you could use this is equal to 0.5. So you know the coefficient of drag. You can calculate what the force is by equating the force with the weight of the hailstone. If you know what the weight of the hailstone is, the only thing that you have to solve for is the velocity. The velocity doesn't turn up in the coefficient of drag anymore because it's in this pressure regime. And so the physical feeling for it is that you have to make the difference distinction, and you can look at it in 12.1, talking about the influence of pressure drag and viscous drag. In this particular case, all of the lofting of this hailstone is the air that impinges on the bottom of it, going to zero velocity at a stagnation point, and so there's a pressure applied to it, and that pressure happens to be what's pushing it up in the air. And I missed something off. Of course, this is the A. This area, in the case of a hailstone, is just the cross-sectional area that it sees, the frontal view as it sees as the air is rushing past it. And so you know all of these components, and so you should be able to calculate the velocity. And if you do that, it comes out that the velocity is about 30 meters a second, 62 miles an hour. If the velocity is less than that, then that hailstone of that particular size will drop out. If it's more than that, it will be carried up into the cloud, and it will get bigger until it's ready to be able to come out. Okay. So that's the essence of external flows. So finally, we can use this idea that you have these two regimes for behavior, where you have, should I just draw it out to the one side, if we have this graph that's split down the middle at basically a Reynolds number of 10 to the 2, that you have this laminar regime, very idealized and turbulent regime. So these two behaviors, that in this region where you have primarily pressure drag occurring, then one opportunity is, since this pressure drag magnitude in terms of the coefficient of drag, for instance, is lower here than it is at these magnitudes, even though it's invariant, then if you're able to, for instance, push it into this region where you not only get this pressure drag, but where you get this dip at this one end, this area here, which is this development of a turbulent boundary layer. So in terms of the behavior that you see here from this diagram, what happens in this particular area is that you have only a very thin slip layer occurring around this. As you go out in the radial direction or the y direction, then the velocity very quickly goes back to the far field velocity here. So it's 0 at this point here, but it very quickly changes, as opposed to this example, where it would transition very slowly back to this velocity. So this magnitude of this change is very rapid in this case. So you get a very thin layer where all the dissipation is taken care of, and it actually turns out to be more efficient in terms of reducing the magnitude of this drag coefficient. And so some sports commodities, such as golf balls, are designed to be able to take advantage of trying to get to this very low friction factor by changing the regime from being turbulent to boundary layer regime, and certainly getting much beyond the laminar regime. And you see this if you look, for instance, at the diagrams that describe the behavior of a sphere traveling through the air. So on the bottom you have Reynolds number. These are high Reynolds numbers, so this is 10 to the 4, 10 to the 4 here, 10 to the 5, 10 to the 6, etc. So it's the right-hand side of this diagram. So in other words, as you look at this diagram that we just looked at, and you look at the laminar regime, going turbulent with this little dip here, and this is Reynolds number versus coefficient of drag, then the part that we're looking at in this diagram is this portion here. So this is this diagram. And see, what you see is that this transition to being this kind of boundary layer flow occurs at a Reynolds number, and if it's a smooth ball, then this transition going from a relatively high friction factor to a relatively low friction factor occurs at quite a large Reynolds number. In this case, something just less than 4 times 10 to the 5 in terms of this non-dimensional number. If you can change the roughness of the ball from being a very smooth ball to being a dimpled golf ball, is what you do is you push this transition earlier. And so if you can't get the golf ball to physically travel at this velocity where it will get to this lower friction factor and therefore fly much further when you hit it, then you try and bring this transition earlier so it develops this boundary layer earlier. It doesn't go as deep in terms of reducing the magnitude of the friction factor as much as it does at this higher level, but what it does is it brings it into the range where the golf ball might be flying. And my guess is that if you calculate from this Reynolds number what the appropriate velocity, and from the size of a golf ball, what the appropriate velocity would be that the golf ball would be flying at, you'd find that typical velocities for golf balls would fall in this range. So having some roughness to it brings this transition earlier and therefore makes it a more efficient way to travel through the air, primarily because in this region with this thin boundary layer, the friction factor that you get is much less than the friction factor even that you get in the turbulent regime, because you're bringing it down to this lower magnitude. So that's one obvious way where our understanding of boundary layers and frictional drag has some bearing on design of golf balls. You can also think about drag that you have when you push a ship through water. And so in this particular case, it might not be appropriate that we use the Reynolds number. But in this particular case, the coefficient of drag that we get is typically a function more likely influenced by the Froude number, which we'll talk much more about in the near future. But as you recall, the Froude number is equal to the velocity at which you're traveling, or maybe your ship is traveling, divided by the velocity of the celerity wave. This is the depth of water. Below the surface. And so this is the velocity of the ship, if you like, divided by the velocity of the wave. And so the wave that's important for a ship when you're pushing it through is the bow wave. And so if you have a bow wave that develops up in front of the ship, then basically in pushing the ship along, the ship has to kind of mount over that. You're actually pushing the ship uphill, if you think. And so if anything you can do to get rid of that bow wave will be helpful to you. And one way you can do that is typically with these bulbous noses on a ship, where you'll dissipate the bow wave will be muted, and as a result, if you look at the drag coefficient due to pushing it through the water, in this case I presume due to viscous forces rather than pressure forces, in that particular case you can actually keep the magnitude of this drag coefficient much less than it would be if you were actually generating a wave at the bow. And so you can take that into design to be able to do that. And of course, we're not the only people who know about that. You know, the First Nation and the Inuit, who used to use kayaks, typically with this nose, kind of alligator-type nose underneath the water, have known about it for centuries, I presume, but I don't know. And so reducing the size of the wave ahead of you also has some influence. So we've talked about the reasons why on this drag versus Reynolds number diagram we have these two regimes where we might find ourselves. The first is this laminar regime, and then the turbulent regime. We've done a couple of examples for each. We did this one with hailstones, which requires one solution. We did this one with Stokes settling. for a different solution. And we also combined them to be able to look at other cases as well where we have Tacoma Narrows. And so this understanding helps us be able to define, in all cases we're figuring out the forces on structures to be able to figure out for Stokes settling what the velocity of the particle is, and then once you know that velocity you check the Reynolds number to make sure you really are in this regime. And likewise for the hail, we use it to calculate the velocity of the air needed to loft the hail within the cloud, and again we have to check the Reynolds number to make sure that it exists in this turbulent regime. The other thing we can use it for is, instead of looking at velocities, which each of these were doing, Hale and Stokes, and I guess the Tacoma Narrows was a frequency of oscillation in our particular case, the other thing we can look at is the forces that are applied on structures. And so, for instance, those are the forces that might be applied on a survival building that a tsunami hits when you've gone up to the 4th floor, and you hope that the drag on the building doesn't knock the building over. Or equally, it might look at the forces that are applied on a water tower, in State College for that matter, when you have air blowing against the water tower. And so in that case, we can look at the behavior in a similar way to the forces that are applied on the structures we've looked at so far, which have been spheres only. But we can also look at structures that are made up of composite components. One might be a water tower, which is a portion is a sphere, which is the top part, and the lower portion is some kind of a cylinder, which goes up from there. So this is this region here. And so the assumption we can make is that these are completely decoupled systems. So maybe if we know what the drag is that's applied on a particle sitting in air with nothing else around it as air goes by it, and also if we can calculate the drag that would occur around for flow around a cylinder. If we calculate what those forces are, then we would calculate, for instance, the reactions that you'd have to apply at the base of this, and also the moment that you'd have to apply to make sure it's static. And so just by statics in this particular case, we can get moments for the magnitude of the loading on the sphere, which would happen at this height, ds, which is a height of the cylinder plus the radius of the sphere. This is the lever arm that acts through. So the lever arm multiplied by the magnitude of the drag force gives you the moment. And the one that's due to the cylinder would be, the force acts at half height. And so the height of action multiplied by the drag force that acts on it. And in each case we can get the drag force of the sphere and the drag force of the cylinder just from the magnitudes of the drag coefficients for each of those structures, multiplied by their appropriate diameters, the velocity of the far field flow, and the density of the fluid which blows over them. And so this is absolutely deterministic, so long as we have a velocity, a fluid density, the geometry of the system, and some drag coefficient, an appropriate drag coefficient for each of these two different geometries, we can calculate what these forces are and add them together. And so the other assumption that's usually made in this is that for most structures, when you're talking about flow in air, then if you're looking at the regime in which we are operating, coefficient of drag versus Reynolds number, then the assumption usually is for air, and you can calculate this, that the Reynolds numbers are high enough that we're always in this region here, and there's a single value that defines that behavior. And so many of these drag coefficients are done for structures in air, and the assumption usually is that the drag coefficient is in the fully turbulent regime, and you can calculate the magnitudes. Once you've calculated the magnitudes of the forces, of course, you can calculate what the Reynolds numbers actually are, and hopefully they're high enough that they satisfy this requirement that they're way to the right of this transitional region. And so you can follow that example just to be able to see that. So it basically becomes a recipe where you take all of these individual components and you add them together. You can do it for the behavior of a car. You can take the front end, you can take the windshield, you can take the roof, you can take the lower rear, you can take the side elevation, and you can add all these components together just by summing them. It's just been done empirically in the laboratory, and by adding these components together for a given velocity, you can calculate what the coefficient of drag would be. And if you know the coefficient of drag, you can always use this expression, the drag force being equal to always a half, just by convention, density of the fluid, the velocity of the fluid squared, multiplied by some predefined cross-sectional area. Usually the frontal area allows you to be able to calculate exactly what that would be. And so it just becomes a recipe, and you get that information applied. And so no surprising that if you look at progressively less aerodynamic and more stubby regions both behind them, and also in terms of looking at the fronts of cars as well, aerodynamic versus more blunt, if you like, that the magnitudes of these drag coefficients should change. If you look at average drag coefficients occurring over the last century, I guess we're almost up to 2020, and how those have changed with the shape of cars, then not surprisingly, if you put a Prius on here, I suppose it would be, the trajectory would keep on going down here. I don't know exactly where we are now, but aerodynamics, of course, is a big thing in being able to cut fuel consumption by making vehicles more efficient. And of course, you can get drag coefficients evaluated for any single shape that you could imagine. Again, they're for magnitudes of Reynolds numbers, so they're in this kind of fully turbulent regime. You see that these are quite large numbers of these Reynolds numbers. And of course, a characteristic length has to be applied to the structure to be able to calculate Reynolds number. So I guess you need to remember two things. The first is that if you're going to use coefficient of drag in some way, then in using this expression for the drag force, which you like to be able to know, then you have to use this expression where this is the far field velocity, and there's typically an area attached with this, and the area would be defined by the particular drag coefficient that you would use. And secondly, when you calculate the Reynolds number is a velocity, a density, a length dimension, and a viscosity. Then you have to use an appropriate length dimension, which the experiments for this particular shape have been scaled with. And so those lengths would be defined for your particular case. I guess in this particular case, these appropriate lengths are the D value, so it should be a D. I just didn't. So in other case, use this value of this characteristic length. So this should be. I just don't want to confuse it with this force. This is a force, right? And you can see that you have these drag coefficients for all kinds of shapes, for beams that would be, for instance, you could use this if you're calculating whether your tsunami shelter, when you're up on the third floor, would actually topple by calculating the moments that would be applied to this and therefore the forces. You could apply it to the helmet of someone on a bicycle with this frontal portion here. Always seems surprising that it's important to have the sharpest part behind, to have this kind of smooth flow that doesn't have any separation as it goes behind here and off to the back, rather than have it maybe arranged the other way. And of course you could calculate, for instance, terminal velocities of someone dropping in a parachute, if you know the drag coefficient for a parachute, if you know the drag coefficient for a satellite dish, or even for a fluttering flag as a function of the length dimensions of this. This is the area in this particular case, and the D, relevant D in this particular case, would be the height of the flag. not its web, I suppose, right? In this. Bikes, for riding bikes as well. So anyway, so you can calculate what the magnitudes of composite drag would be for all the things going through to apparently a dolphin or a tree in this particular case. So that's our understanding maybe of looking at drag. We don't necessarily need to repeat all the same things for lift, but just to realize that the only difference between drag and lift is exactly the same expression, but the only relevant difference between those two things is if you're looking at an airfoil, that there are a couple of things to remember. One is that relative to the flow velocity, there'll be a magnitude of drag on that airfoil, and there'll be a magnitude of lift. The only thing that differs from them is that one is in the direction of flow and one is perpendicular to flow. And also on the same chart of Reynolds number versus, in this particular case, coefficient of lift, you'd expect to see these two regimes where you have a change in Reynolds number. Maybe it's 10 to the 2, maybe not. But in this case, all of the lift is due to pressure changes, destroying velocities, and in this case it's due to viscosity effects. And so you can imagine as fluid goes past this portion here, there's a small feature of shear stress, which is pushing up in the lift direction, but most of the lift really comes from the change in velocity between the underside and the upper part, where you have a larger pressure acting on the bottom than you do on the top, and so there's a net lift force that's arranged just by the mismatch of those two pressures. And this effect is due to the mismatch in pressures by the changes in velocities that occur around here, not due to this small portion of shear stress, which will be very small by the time you get here. And so, not surprisingly, planes lift as a function of the Bernoulli principle. You could imagine part of it's the Coanda effect, but mainly it's the Bernoulli principle. And you can run experiments, as you've seen in the previous videos, in wind tunnels to be able to measure this magnitude of lift and to scale between a model and a prototype to be able to figure out exactly what's going on. Okay. So anyway, so I'll let you look at the material on lift. You can calculate it analytically. You can calculate it in the wind tunnel to get this magnitude of lift as a function of a measured parameter. And the final thing that we'll talk about are rotational flows. We talked about this in terms of streamline behaviors when we were discussing behaviors for streamlines with injection wells and recovery wells, that we could actually add two flows together. So we could get a far field linear flow flowing past a wing. We could put a rotation on top of that, and as a result of that we'd get some composite flow that would occur. It's kind of beyond this class, but it turns out that if you want to get actually reasonably good analyses of the flows around airfoils, then you have to actually make this substitution for this rotation to be able to get decent predictions of what the lifts would be. And so it doesn't affect the magnitudes of the forces that you'd measure in a wind tunnel, but if you're trying to get these magnitudes of forces by developing streamlines, figuring out along these streamlines what the distributions of fluid pressures would be on the top of the wing versus on the bottom of the wing, and looking at the net force that's applied to figure out what the magnitude of the lift is, then you have to make some correction in the flow regimes. So we don't have to worry about it for this class. But the point is, in the same way as we talk about forces on structures due to drag, you can make the same calculations with lift for wings. And it would be a rare occasion where we don't have one group talking about why a baseball ball rotates when you put spin on a baseball ball. It doesn't have a straight trajectory anymore. And of course that, well, not of course, but that is due to lift as well. And so the basic idea is that if you think about a baseball ball, a static baseball with flow around it, you have a stagnation point here, a streamline that goes around to the back of it, and a separation point at the back. And so in this regime, the forces that you'd expect to have due to lift would be exactly the same on this side as they would on this side, just because it's symmetrical about this midpoint. And so there'd be no net lift that's given to this. There'd be some pressure drag by the fact that you're stagnating here, but in terms of lift, as this static ball sits here and the air flows around it, or alternatively, you have a ball physically moving in static air, be exactly the same behavior. You have no net lift between the top and the bottom. So this is a plan view, if you like. It could be on a baseball. If you spin the ball, what you'd expect to see would be that the velocity that you'd have at this boundary, so if this is the velocity versus radius, then you'd expect to see something like this. The ball grabs the air where it contacts it, and the ball is spinning at some rotational velocity omega in terms of radians per second. So this boundary here, the air is being dragged with the moving ball, and it's going at some relatively big velocity. As you get further away from the ball, then the velocity at the far field is 0. And so you have this change in velocity as you go away from it. If you add these two regimes together, then the flow regime you get is this. So you get the, for a rotating ball, static ball with air flowing around it, it's perhaps easiest to think of it, then this is one flow line. This is a stagnation point. So part of the flow goes along the top and then sheds off of this separation point here. And a portion of the flow goes around the other side and also sheds off here. And so since the molecule of air that started off here and ends up here has to have departed from a molecule of air here and join up here, this velocity by definition has to be slower than the top one because it's traveling a smaller distance in the same time that it takes to go to the top. So the fact that they travel the same time path but a longer length means that this velocity is higher on the top. And we know from just Bernoulli's relationship that if we have a larger increased velocity, then we'll decrease pressure. So they start off at the same pressure here, and so the pressure trajectory as you go through here has to be larger because this is a higher velocity. If you have a higher velocity, the pressure has to be decreased, so the pressure acting down here has to be less than the much bigger pressure that's acting up here. So the principal lift. So this is, if you think about it, a wing. It's exactly the same principle that a wing works with. And so from this point of view, there'll be a net force. If there's a net force, you'd expect this to go up. And so if you imagine this as being a static air, but you throw the ball in this direction, so if you're throwing the ball in this direction and you're spinning it backwards, then you'd expect in this particular case to have upwards lift. And so the trajectory the ball would take would be in this particular direction. And of course it's kind of backspin. I think if this is the vertical plane, then this is backspin, and if you're putting the spin on it, it goes upwards. And if you're putting the spin in the opposite direction, so it spins forwards as it flows. So this is the ball, and it's spinning in this direction. Then it would go either downwards or upwards if this is the vertical section. I drew it this way because this isn't very helpful because it kind of seems like it's going in the opposite direction. But if the ball is spinning backwards, has more pressure below it than above it, it will go upwards, and it will tend to spin in that direction. And so you can calculate the magnitude of that particular spin. And you can classify that, of course, right? You could do an experiment in the wind tunnel. You could take a ball, a sphere, and you could spin it at some velocity, and you could measure as you flow air across the top of it, you could measure the magnitude of the force that's applied upwards to it, and then calculate the magnitude of either the drag or the lift as you flow air over it at some particular Reynolds number. So this is just the results of having a ball within a wind tunnel. You have a given velocity that's applied to the air that goes past this ball. Because it has a given velocity, it has a given Reynolds number, which you know, which is this particular magnitude. And now, if you spin this ball at some rotational speed, this is radians per second, as you increase the rotation from 0 through to some number, the magnitude of lift changes. At 0 rotation, from what we said before about the symmetry of this is 0 rotation velocity. It's symmetrical above and beyond. The pressure acting upwards has to equal the pressure acting below. So there's no lift. There will be some drag, but no lift. And you see that exactly at this point here. At no rotation velocity, there's no lift, but there is some drag that's applied to it. And as you increase this rotational velocity, then what happens is you increase the amount of lift that's applied to this. So this is coefficient of lift. And so at this non-dimensional rotational velocity, this is a diameter, and so radians times diameter is a length, right? So we can check that this is just a non-dimensional number over 2 times velocity. It doesn't matter about the 2, but if you look at the units for this, this is radians a second. This is length, so it's meters. And radians per second times a radius gives you a velocity. This overall is a velocity, and it's divided by 1 over 2 times a velocity. So between it all cancels out. So velocity on the top, a velocity of airflow horizontally on the bottom. I guess this is u in this particular case. And so this non-dimensional number is non-dimensional, and so you can look at the magnitude of the lift that you'd get as a result of this rotation. In this particular case, if it's rotating that way, the lift would be in the upwards direction. So this would be the direction of the lift in this particular case. And so if you know the rotational velocity and you know the velocity of the air that's going over the ball, you can calculate the magnitude of the lift. And if you know the magnitude of the lift, you can calculate, you could calculate whether it's going up or down, and also the rate at which it extends, because we know that, for instance, force equals mass times acceleration. This is a force. This is a mass of the ball, and of course you could calculate the vertical acceleration that you'd get in that particular case. And I think there's an example done that does exactly that. It takes a tennis ball, a table tennis ball that has a particular weight, has a diameter, and is hit at some velocity in the air, so it's moving at 12 meters a second. And you put backspin on it by chopping it, I suppose, right? If you chop it, you'll put backspin on it at some angular velocity. And so that angular velocity will cause it to rise due to this rotation. And the question is, what's the value of rotation you have to apply if you want this to go on a horizontal plane? The vertical drop is going to be driven by the fact that gravity is acting downwards, and you have this acceleration or this force that's acting upwards. So this is force equals mass times acceleration. This happens to be gravity that's making it go downwards. So to counteract it to go up, you have to operate with a force on the ball due to spin, which is going upwards, which directly counters gravity going downwards. So these forces have to be equal and opposite. And so the force that you apply due to the spin has to be equal to the weight. So the weight of the ball and the lift. So in other words, the weight of the ball versus the lift that you're applying to it have to equal each other. And we know that by rearranging this expression for the coefficient of lift as a function of the lift force times rho v squared times a, we can rearrange that into this, where we know the density of air, we know the ball's moving at 12 meters a second, we know the cross-sectional area of the ball, which is just going to be this frontal area, and we know the coefficient of lift, so long as we know what the Reynolds number is, right? We could go back to this thing and we could figure, so long as we know what the particular Reynolds number is, we could calculate what the coefficient of lift would be for this chart. So I'm presuming that the magnitude of the Reynolds number in this example is actually 6 times 10 to the 4, because that's what's given here. Does it do the calculation? Yeah, for standard fair conditions, it must be that that's the case. We can calculate the magnitude of this coefficient of lift from the weight of the ball, density of air, 1 kilogram per cubic meter, the velocity the ball is going at squared, the frontal area of the ball, which is just in terms of diameter, and we get the magnitude of the coefficient of lift as a function of that. We need to calculate what the magnitude of the rotation would be to be able to get the magnitude of the lift that we need in this particular case. So we know that in spinning the ball, the weight has to equal the lift. We know in this expression everything to be able to calculate exactly what the coefficient of lift has to be, because we know the weight of the ball, we know the diameter, we know the velocity at which the ball is traveling, and so we can calculate what the coefficient of lift is that we need. If we calculate this 0.244, this is 0.2, this is 0.4, this is 0.3, I suppose this is 0.244. If we go across here and come down here, then the magnitude of this value of this dimensionless parameter is about 0.9. And so we know that that has to equal this, and the only thing we don't know is the magnitude of this rotational velocity, because we know this is 12 meters a second, and we know this is the diameter of a ping pong ball. And so if we have this expression and we solve for the rotational velocity, then we end up with whatever that is. And if you convert that rotational velocity in revs per minute in terms of the appropriate diameter, just in terms of 2 pi radians is equal to 1 revolution, then we have the revs per minute that are required to be able to do that. And so that's just another example of being able to use our understanding of lift and drag to be able to look at these behaviors. And again, you can look at separations on these things. So that's an interesting example just to close out on. So to recap, it's probably worthwhile doing these, just making these few points. The important behaviors for us to understand are that when we look at lift and drag, they're very similar to each other. All that's different is that in lift, we're looking at the force which is applied perpendicular to the flow direction, and drag, it's the same direction. The components of this behavior are due to pressure drag at high velocities and due to viscous drag at low velocities. The behaviors relate directly to viscous drag being related to viscosity through Newton's law of viscosity, and the pressure drag by killing velocity, which gives us pressure that's applied on the system. Both components are always present, but some might be dominant in different regimes, and although both are present, then at low Reynolds numbers, viscous frictional drag dominates, and at high Reynolds numbers, where it's turbulent, pressure drag dominates. And by knowing something about the Reynolds number at which our experiments or at our prototypes are running, if we can get a magnitude of this coefficient of lift or coefficient of drag, then we can directly use that to calculate what the forces are that are applied on the structure just by using these relationships, which are mirror images of each other. The coefficient of drag being related to a force, a drag force, an airflow velocity, a density of the air or fluid that's flowing around the object, and an appropriate cross-sectional area. And likewise for lift, same expressions, a lift force, an area of flow, planiform area, the frontal area typically, or for a wing it would be the plan area looking down on a wing, the velocity at which the fluid is traveling, and the density of that fluid. And the other important component is that this is nothing different from an Euler number, because this force over an area is just the same as a change in pressure over density times velocity squared. And just by convention, when these measurements are made for these coefficients, we use the half term in here primarily because it just turns up in Bernoulli's equation. That's all, just by convention. And so that's the essence, if you like, of when we're talking about flows, is to realize that it fits in these two regimes, and to solve problems in these different regimes, we have to take a slightly different tack to be able to solve for the things that we want to know. In this case, we're interested in knowing the velocities of the flows that we'd have, but in other cases, such as when we deal with composite drag, sometimes we're interested in the forces that get applied on structures, and we can apply those structural shapes, add them together to be able to get the correct behavior. Okay, so I'm going to leave it at that. Thank you very much.